Hello and welcome back. In this second section of lesson 1, we'll be learning about the concept of generational garbage collection, what it is and how it helps in implementing effective garbage collectors. We'll also talk about the different memory pools that are available in the HotSpot JVM. In the generational garbage collection, memory space is divided into various generations, each generation holding objects of different age ranges. The age of each object in the young space gets incremented each time the space is swept over by a garbage collector. Objects that reach a threshold age are moved to the old generation. Generational garbage collectors are implemented based on a hypothesis that most of the objects allocated in an application or a program die soon after they are allocated, or in other words, the objects die young. And very few references exist from the older objects that have stayed around longer to the younger objects. Following this hypothesis, in the HotSpot JVM, the heap where the Java objects are kept is divided into two generations, young and old. The young generation is often small and is collected frequently. The old generation is larger, is collected infrequently, and fills up slower. When the young generation becomes full, a minor collection is induced that collects only the young generation. The old generation is not collected with minor collections. Since the young generation space is usually small, these collections are also fast. When the old generation fills up, it causes major or also called as full collections, in which the entire heap is collected. Major collections last longer than the minor collections because these need to go over the objects in the entire heap. This picture shows that the Java heap is split into two generations, young and old. It shows both the committed and the virtual space in the heap. At initialization of the virtual machine, the entire space for the heap is reserved. But depending upon the heap parameters provided to the JVM, not all of the space that's reserved may be immediately committed to the virtual machine. The uncommitted space is labeled virtual in this picture. At runtime, different parts of the heap, tenured and young, can grow to the limit of the virtual space as needed. The young generation consists of Eden and two survivor spaces. Most objects are initially allocated in Eden, and the surviving objects are moved to one of the survivor spaces. One survivor space is empty at any time and will serve as the destination of any live objects remaining during the next young collection. The other survivor space contains objects that survived the previous collection but are still too young to be promoted into the old space. Objects are copied between survivor spaces in this way until they are old enough to be copied to the old generation. This illustrates the allocation and promotion of objects in the Java heap. Allocations happen in the young generation, and the objects that grow older than a threshold age, which means that the objects that survive a certain number of garbage collections in the young generation are moved to the old generation. Prior to Java 8, HotSpot had a third generation, called the permanent generation. The JVM uses an internal representation for Java classes and their metadata, such as methods and field symbols, bytecodes of methods, and static field values, etc. In Java versions prior to 8, the representation of classes and their metadata is stored in the permanent generation. In turn, strings are also stored in this space. The space of this generation is contiguous with the Java heap. Since JDK 8, the JVM does not have the permanent generation. It has been replaced with a new space called the meta space. Classes and their metadata are stored in this new space. Unlike PermGen, it's not contiguous with the Java heap. Metaspace is allocated out of native memory, and since it is allocated out of native memory, the maximum space available to it is the whole of system memory. But we can limit it using the JVM option max metaspace size so as not to allow classes in a single JVM process to accidentally use up the entire system memory. The JVM has two important features whereby it uses 32-bit offsets to represent 64-bit pointers on 64-bit platforms. This is done to gain some performance benefits and to reduce the memory footprint. These features are compressed OOPs for having compressed object pointers and compressed class pointers for having compressed pointers to classes. Now when the JVM uses compressed classes pointers to represent 64-bit pointers, it uses a separate region in the metaspace to store the class metadata which is referenced by these compressed class pointers. And this region is called the compressed class space. By default, 1 GB of address space is reserved for this compressed class space. So the metaspace is the combined space of these two regions used for storing metadata and the compressed classes. Without compressed classes pointers, classes and their metadata are stored in the metaspace. The class pointers in objects in the Java heap are 64-bit pointers on 64-bit platforms. When the JVM option compressed classes pointers is used, the compressed class space is used to store the class metadata. Objects in the Java heap now have 32-bit class pointers, and that point to the classes in the compressed class space. The metaspace now contains only the other metadata, such as methods, bytecodes, constant pool, etc. The code cache is the space where the compiled and the optimized machine code generated by the just-in-time compiler is stored. It's allocated out of native memory, and the memory of the space is managed by the code cache sweeper. The sweeper keeps track of the references coming into the compiled code, and if a piece of compiled code is not referenced anywhere from the heap and is not being run by any threads of the process, then it is swept and removed by the sweeper, and the memory used by it is added to the available free memory of the code cache. Native memory is the rest of the available system memory. It's not managed by the JVM but by the operating system of the platform. This snapshot gives a quick view of the memory pools available in the HotSpot JVM. A tool called the JMX console, which is part of the Java Mission Control shipped with the JDK, is being used here to monitor the memory usage of a Java process. As we can see, this tool can show the available memory pools, their capacity, and how much memory is currently being used in these pools. This picture shows that the Java process is running with the parallel collector, one of the garbage collectors offered by the HotSpot JVM, which we would be talking about in our next segment. Here we can see that we have Eden and Survivor spaces, which are part of a young generation, and other spaces, old generation, meta space, compressed class space, and code cache. To summarize, the HotSpot JVM divides the managed memory space where the Java objects are kept into generations called old and young generations. Objects get allocated into young generation and then are moved to the old generation when they reach a certain age. Then there is a region managed by the JVM where classes and their metadata are stored. Prior to JDK 8, this space was called permanent generation. In JDK 8 and onwards, classes and their metadata are stored in metaspace. Metaspace, unlike permgen, is allocated out of native memory. There's a memory pool called the code cache, where the code generated by JIT compilers is stored. And native memory refers to the rest of the system memory, which is not managed by the JVM. That brings us to the end of the section 2 of the first lesson. Thank you.